In this lesson, we are going to use our knowledge of trig functions and sinusoids in particular to look at rational period trig equations and some applications. So y equals sine x has a period of 2 pi, which is irrational. So to have a rational period, our equation is going to have a pi in it, and you're going to see that, and keep that in mind when you think about the differences of what you've seen in trig equations before versus what I'm about to show you now. So the first one, I'd like both a cosine and sine equation given a min and a max. Here's 1, -1, and 10, 3 right here. Okay. First of all, the amplitude. The amplitude is found from the difference of y values divided by 2. The vertical displacement is the mean value, so it's the sum of the y values divided by 2. The period is twice the difference from the max to the min, or the min to the max, so 18 is the length of the entire function, so we're representing only half of it right now. Now, a quarter of the period, in this case, is 18 divided 4, or 4.5. I'm going to use that, 1, 2, 3, 4.5, to just take note of where the mean value is located. So the function falls to the mean, continues falling to the trough or low value, and starts coming back up. And I'm just going to plot a couple of reference dotted lines. This is the mean value of the function. This would be the peak value or high point, and the trough or the low point at -1, 3, and 1. All right. So if I were going to do a cosine equation, I would refer to point A, because that's the max value. I would write the amplitude of 2, cosine, and I need to figure out the period. It's 18, so I'm going to write 2 pi divided by 18. And the max value is normally located on the y-axis, and it's been translated 10 units to the right, so it's a phase shift of 10 to the right. There's my vertical displacement. Now, this is the period when the b value has 2 pi in the numerator. Remember that b is 2 pi over the period, or period is 2 pi over the b value. All right. If I were going to write a sine equation, I would use point B, the mean rising value. So for this, I'm going to write sine. The amplitude is unchanged. The period is unchanged. The phase shift differs. Vertical displacement is the same. The phase shift is based on, I noticed I used t here for time. I'm not doing an application. That should be x. There we go. The phase shift is to the right. This mean value is normally at the origin, and it's now 1, 2, 3, 4.5 units from 1, or 5.5 units to the right. Now, I could talk about a falling value of the mean over here, or I could talk about the minimum value as well. If I refer to the min value rather than the max, the function is going to be exactly like above, but have a minus sign because of the reflection. I almost said reflecting the reflection. It's also going to be impacted by a different phase shift because I'm only 1 unit to the right now. Or if I referred to D, a falling mean value, again, it's a reflection rather than a rising mean, falling mean. Most of the details remain the same. It's only the phase shift that's going to vary. Now this is 4.5 units from 10, so 14.5. And that 4.5 units was a quarter period, because that's how I break up my 4 quadrants, representing rise from mean to max, max to mean, mean to min, and min back up to mean. So those are 4 possible equations for that one graph. You can graph them on your calculator with a suitable window and confirm that that works. Notice also, before I move on from these, that the period was not pi-based. It was rational. The coordinates on x were also rational. This was 1 unit. This was 5.5 units. Okay, there was no references to pi anywhere. This is often the case when we actually work with cyclic phenomena, or phenomena that have a period and repetition. Things like Ferris wheels, things like tides. When we talk about how long it takes for one complete cycle, we seldom refer to pi. Here's an application. There's a car engine that's idling at 1200 RPM. It's a little bit high RPM, but it'll serve our purposes. There's a piston, that's a moving part in the engine, and it rises and falls inside of a cylinder. We're told that it's 16 centimeters from the bottom at its highest point, and 2 centimeters from the bottom at its lowest point. And we'd like to write an equation for height as a function of time. Okay, well, I'm going to make a quick sketch of this. And I'm not going to worry terribly about the scale. I'm just going to try to represent the information fairly accurately in terms of a sketch. Okay. Let's assume it starts at the highest point. I think it actually says that. The piston is at the highest point to start. Yeah, so it's at a height of 16 at time 0. All right. It's at a low point of 2 a little bit later. I'm going to just make some reference dotted lines to help in the sketching of a sinusoid. And I need to use that 1200 RPM, and from that I'm going to get my period. So RPM means revolutions per minute. So if I want to talk about revolutions in a second, what I'm going to do is I'm going to change to seconds by writing a ratio of proportionality, which means I'm dividing by 60 in this case to convert to seconds. So let me see, that's going to be drop a 0 with a 0, 120 divided by 6 is 20 revolutions each second. Now, this is the frequency. This is how many events in 1 second. The period is 1 over the frequency. So it's 1 over 20, or 0.05 is my period. So if I want to represent the next value, 2, 4, 6, 8, let's just use this for convenience. My next peak is going to be at 0.05 seconds, which is very fast. 1, 2, 3, 4, 5, 6, 7, 8. So if I go halfway, 0.025 is where it hits the minimum. Now my mean value is right in between, and right in between. These are my mean values. That's going to be 0.0125 and 0.0375. Yeah, let's smooth curve through those points. So there's a representation of a little more than one cycle of the travel of the pistons. All right, if I want a cosine equation, I'm going to refer to point A, the max. Now, let's figure out my amplitude. My amplitude is the high minus the low divided by 2, which is 7. My displacement is the average value, so that's 9. I got my period. My B value is 2 pi divided by my period, which I could write as 40 pi, or 2 pi divided by 0.05. Now, I'm going to keep it as 2 pi divided by 0.05 because that lets me see the period quickly, although 40 pi is a tidier way to write it, so I'm good with either one. Anyway, height output comes from time input, 7 amplitude, cosine for a max. So there's my 2 pi, there's my period. Now, my time value has no phase shift, so minus 0, which I don't even have to write. And my vertical displacement was 9 units up. So there's how to write one from A. Now, from B. B is a rising mean value. Height of time equals 7, no change. Sine, because I'm using mean. Period doesn't change. The only thing that changes is the phase shift. In this case, I've shifted over to the right 0.0375 seconds. If I want to write a C and a D equation, C might be for the min, and D might be for a falling value. Pause and try those, and then compare your answers to mine. All right, there's your result for the cosine. If I'm using a minimum, it's reflected. Note the minus. No change in amplitude, no change in period, no change in vertical displacement, and now I'm negative because it's to the right, or subtraction, 0.25 representing where the min value is. Now try the sine. And there's your sine equation. Notice this is a mean value that's falling, so I use a minus sign here, and the 0.125 to the right, which is minus. So there are four possible equations. Another one of interest would be over here at the next max. That's another cosine. It's maximum, so it would be plus, no reflection. And I'd use the decimal 0.5. That would get me yet another equation. There's a few examples to give you an idea of how to write rational period functions. Note that the pi rather is right in the b value when the period is rational. And those apply to many situations in real life. Good luck with working on some problems related to this.